is. All right. So let's begin because we have a huge ground to cover today. We will talk about decorators, list comprehension, generators, context managers, and functional programming. These are all a bit more advanced topics than previously. And feel free to stop me whenever you feel like you have a question. All right, let's start with the imports and decorators. We have already met with a couple of decorators yesterday, static method, class method, property, data class, and so on. These were all so-called decorators. And let's see how we can build our own decorators. You can create a function within a function, and that function within it can also be the return value of the parent function. And you can access the inner state of the parent function with the child function. So you can see we define this parent function, it gets a parameter, and we can access the value of this parameter. And we can create a so-called function factory by returning the child function from the parent function, and then we can use this return function however we would like. We can also, you have seen this before, we can also pass a function to another function as a parameter. We can use the child function inside to do other stuff with this function. So we will wrap it inside other functionalities. And then we can return this wrapped version of the original function in the parent function. And you can see here, we use the add noise on this noiseless function. And what it will do is that we add this part to this noiseless function when we are running it. So it will be surrounded by the wrap noise. And this is actually kind of already a decorator, because a decorator is a function or class that takes a function as an argument, and it wraps it with additional stuff. And this at function name is just a kind of nice syntactic sugar, or shorthand to write these kind of method calls. But in the background, this syntax is just the same as writing it this way. Another thing that decorators can take parameters. We have seen this with the data class previously. So a decorator can have however many parameters as you would like, and it can wrap our function with accordance to the given parameters with additional functionality. And you can also define decorators as classes. And in this case, we need to implement a call function inside the myDecorator or inside the decorator class. And this call function will be called when you apply the decorator class to the function that you want to use it on. In general, you probably don't really need to know how to write decorators at the top of your head, but it's very important that you know how to use them, because there are a bunch of libraries, like, for example, click here, click, that use this decorator syntax to provide additional functionality to your functions. Click is specifically an argument parser. So when you are running your code from the command line, you can add arguments to the run, and this will recognize that you've chosen this option. Then we will set certain things inside the wrapped function according to these outside things. All right. This was a very quick rundown of decorators, and there might be questions.
What are the benefits of using them instead of not? What do we get?
The additional functionality. If we go back to like the previous lecture and the data class, the data class decorator added additional functions to our class that we didn't have to implement. Or in this package that I was trying to show you in the very overview, you can pass arguments directly to your function from the command line, which is very useful when you are running things this way. You don't need to configure it differently, just like you would call a C++ function similarly. Are you convinced?
Yeah, thank you.
Thank you. All right. That's all about decorators. There won't be exercises concerning decorators in the assignment, so it's all in the lecture. Read it at your own pace if you would like to get some additional information. So let's get on to list comprehension. We have seen that we can define for loops this way. We can create the insides of a list using this for loop and the append function or method of the lists. But we can do the same thing in one line as well. And this one line follows the following syntax. You have the value that you want to insert. You have the for keyword. You have the iterator variable, so the name that you use for the iteration. And you have the iterable at the end, like a normal for loop. This is the exact syntax of that. And you can actually define an if condition. So maybe you don't want every element in this range to be part of the list, but you only want to have the elements that are even. And in that case, you can say that you only care about numbers that are even, and then you can get the this list with the following condition. It's exactly the same as this, just in a shorter form, and it's nice, concise, and Pythonic. There is no else in this conditional filtering method, but there is this way of defining if-else condition in the variable part or the return part of the comprehension. It's the same syntax as you've seen before with conditional value setting, I think, in the first lecture. Yeah. You can use multiple for loops in a list comprehension as well, and you can see that it will go first on this. So we will iterate over this list, and inside of that iteration, we will go through the elements of the second iteration. So if you would have a matrix like such, you can iterate over that using the same syntax. Let's see what is the type of this comprehension. It's a generator, and generator expressions are very useful for memory, for optimizing memory usage, because you don't use up a lot of memory if you just define a generator. So let's see how much memory would it use if we would define this in a list. So the generator is automatically converted into a list, so it generates it all at the same time. And if we would just use a generator, then the memory usage should be way lower. Exactly. So if you are using a generator inside sum or max or a similar function, it won't generate all the variables inside at the same time. It will just generate it once they are needed. And it won't take up that space in the memory at the time of their usage, or not the whole space that a list would take up. But since these generators can only be traversed once, or they don't take up memory, they can only be traversed once, and once they are done, they will, if you would try to call the next element in the generator that's already run out, you would get a stop iteration exception. if we would try to call next. And you get this because the generator has run out of the numbers that it can generate, or the list elements, even if it's not a list. So what I'm actually talking about here is the iteration protocol that is used in Python. You can define an iterator by overriding the iter function and the next function. And inside the next function, you should have a stop iteration error if someone tries to run it for longer than it should run, or if someone tries to call the next on the iteration when all of the iterable elements have been created already. Yes, minimum, maximum, and sum all support the iteration protocol. So you don't need to call these on lists, sets, or generated object. You can call them on generators themselves, and they can traverse the iterators on their own. And it won't cause any problems. It's more memory efficient if you do it this way. Jumping back a bit to comprehensions. So other than list comprehensions, there are set and dict comprehensions as well. You can define it using curly brackets, but the syntax is still the same, just inside a different type of bracket. The dictionary is a bit different because you need to define key and value pairs. But that's the remaining syntax is the same. The only change from list comprehension is this part. And it's similar to defining a dictionary by hand. And you can generate like a easy, quick counter this way. And these are all generators. The yield keyword is somewhat similar to return, but it does not end the run of our function, but it transforms our function into a generator function. And yield actually gives back values over time. And let's see an example for this. So we define this German vowels function, which will yield one vowel at a time. And if we see it, it's a generator, and we need to traverse it using this, using a loop. And we can loop over the generator's items. Similarly, in this case, it will yield it one by one. And if you would create an instance of this German vowels function, it's a function here, and you try to go over the elements in this first line, you get all of the elements, but in the second iteration, you've already run out of the elements in the generator, so you won't get any new elements. If you would try to force
Sorry.
it to, yeah.
Could you maybe slow down a little bit? I'm having quite a hard time even reading the code so fast when you're scrolling down that I cannot even follow your explanations and reading the code simultaneously. And in the chat, maybe others also have the problem.
Oh, I'm so sorry. You are right. I'm going too fast. Shall we go back to maybe the yield keyword at the beginning of this little section?
Yeah, that would be nice. Yeah, thanks.
All right. So you know that using the return keyword, you can return a given value from a function, and that will end the function. So if this would be a return, this for loop will stop at the moment you returned it. So at the first element, it won't go further than that. Let's see what it would do if we would just return it. So it would just give us the first element. But since we are yielding it, it won't stop the run of this code block. So once it yields it, and maybe it's called the next time, then we will start back up at the same spot after the yield and go into the next iteration of this for loop. So let's try to call it 2 times. Let's create an instance of this and call it 2 times. Oh, yeah. I should iterate over it. But we can stop it early if we would like. We can enumerate on it if you would like to see the indexes of it. And you cannot do this if you would just return the first value in here. All right. The type of this function is a generator. And I have shown an example for this. And if you run the dummy generator, let's add enumerate to this so you can see that it's not returned at the exact same time. So using this example, we can see that we try to iterate it 1 time. It will yield this one. The iteration stops here. Then we call the function iteration again. It will continue right where it left off. Then we go in again. It will find the last element. for the last yield, and it will stop there. And if you create a generator like this, you will see that you can traverse it once, but you cannot traverse it again. The same generator object cannot be traversed again.
Is there a possibility to count how often such a generator was already called? So I always get a different value back in the dummy generator, but do I have the possibility to see the current state of that dummy generator, that I say, okay, it was called twice?
In a way, in this exact example, the enumerate is a good function for this. If you just want to see in which iteration you are in, because it will also give you the index, so to speak, in this case. So the first iteration will have the index 0. The second iteration will be index 1.
Yeah, but a generator doesn't have a built-in count function in a sense that I can get the value.
Not necessarily, but you can define your generator that way if you would like to. So if we would go back to the vowels example, we have a set here, but if you would like to, you could define it as like a dictionary, and you can yield the key and the value pair simultaneously from this dictionary.
Perfect, thanks.
All right. So if we create this generator function again, we can traverse through this again. And if we try to call the next element over and over and over again, so in a while through loop, after the last element, we should get a stop iteration error. And because we have run out of the possible generatable elements, and in that case, in this particular example, we just write out that there are no more elements. And since we can traverse it only once, if we try to generate a list from this generator, the first list will have the elements. But the second time we try to generate the list from the same generator, we don't have any more elements, so that list will be empty. It's the same principle as traversing it. But since you can create multiple instances of this generator object, if you create another instance and try to convert that one to a list, you can do it without a problem. You can also define an iterator with memory. And by that I mean, since you go back to this after the yield, or in the iteration, you go back to where you've left off, you can preserve the previous element in some kind of memory. So you can yield it again if you need it. There will be an assignment that uses this logic. You will need to define a function that can have a particular size of memory, but the logic behind it is the same, that you can do stuff after the yield and keep your
I'm sorry, is this now an iterator or is it a generator? Because it has the keyword yield.
It's a generator, sorry. But it follows the same iteration protocol.
But it would always start at the first item when I call it. That's
when
what
you
this
first,
is doing.
When you first call it, it will start with the first item. But you could maybe stop in the middle. So let's see. Let's define something that we will go over. Oh, I need to refactor this a bit to show that to you. So let's call this a gen. We will go over gen. And let's say we have E, and if E is bigger than 2, let's break. And after this, if you try to start the iteration over, it will continue from the previous step. The memory is lost because of this iter with memory. If I were to remove that, nothing will be lost. But this iter with memory is taking an iterator. Does this answer your question?
Yeah, and I think I don't really understand what it means, or what's exactly the difference for a normal generator. So the difference would be that if I would call a normal generator the second time, even though I haven't printed it completely, it would be empty. And this one still has the rest that it hasn't printed yet or yielded yet?
Yes, maybe this iter with memory is messing a bit with the thing, because it will restart, because that's the creation. So we iterate over the generator function, or the generator, until a certain point. We stop, and it will remember that, sorry, I'm going back to the iterator that we are, or the generator that we are using. So we have only gotten to this point. So we are standing here in the however many iteration, and then we call this again, or we try to access the next element of it again, and it will know where to jump back to.
If we would not have this wrapper, what would it do then?
In our example, this iter with memory was the wrapper. I'm not sure. So if we would have a list here instead, if that's the question. So if we generate the list already, then it will start the iteration, stop after a while, and when we iterate it over it again, it will start again at the beginning.
Okay, I understand. Thank you.
All right. So we can use these generators if we want to try to format our code. You can use such an object in join, for example, and then you can join together list elements by iterating over them or generating a generator from the list. Because as we've seen before, a list comprehension or any comprehension is just a generator. And using this formatting, we can print the list elements out in a pretty formatted way. All right. Questions about generators. You will most likely encounter functions that use this syntax, so generator functions. It's less likely that you will have to write iterator classes, but generator functions are commonly used. And list comprehensions and dict comprehensions are also very useful in Python.
Just a quick question. For the first application example that you used for string formatting, is it cleaner or more efficient to do it that way, or to use a map, for example, on the numbers list to achieve the same goal? What is better between both ways?
Since in this particular case, the memory is already taken up, it's not a big advantage to use it this way. But if we would stream the contents of a bigger file, then it would be better to do it with a generator. Also, if you want to add additional things to your list, for example, in this second example, in here, we want to iterate over this list, and we want to print out the index as well as the element. And you can do it with a generator that won't create a big dictionary beforehand to store your index and shopping list element pairs.
Okay, yeah, that makes sense. Thank you.
That's one of the big advantages of using generators. I will go back up a bit because you were right, I was way too quick at the beginning. So the first example here, where we measure the memory usage of the list version of the same expression and the generator version of the same expression, you can see that it's 5 times as much if you in this particular case, if you try to get all of the elements at the same time in a bigger list. All right. Questions about list comprehensions, generator expressions. Generators. All right, then I think we are.
A question.
Yeah.
When would I use list comprehension? Because it seems like it's harder to read and maybe even slower. So I don't really see the point in using them.
List comprehensions are actually very common. Again, I will go back to an example that, for example, in this case, you have to iterate over a range of 10 and create list elements based on this. But it's a long form to do this. You can write it out in just one line of code. It's the Pythonic way of, if you want to do something simple like this. If you want to do something more complex and you need to iterate over it multiple times or something, then yes, you can use this easier method with the append. But in this version, you create the list in place. You don't need to append elements to it.
Okay.
And also, it's very concise. And if you get used to the syntax, it's very readable as well. And it always follows this something that we want to put in the list. It's for loop and maybe a condition at the end. So we can filter out elements that we don't want. Okay. Can we go to context managers?
I would have a question for set comprehensions.
All right.
So you talked here about set and dict comprehension, but I don't really see. I'm sorry, I was a bit late today, so I missed a lot. So, and I don't really understand what is the set comprehension in these examples, or where is it found? I only see the list.
Yeah.
Comprehensions with the curly brackets, but not the set version.
Well, so this is the list, the original list that we use as the thing that we want to iterate over. This is our little iteration part, like in the case of list comprehensions. And this is the element that we want to put into a set. And it's a set because of the syntax. So sets can be defined with curly brackets. So this would be the same as writing it in this syntax, apple and whatever. It's the same thing. And if you do it this way, this generator will be converted into a set. And that set will only contain one apple, one plum, one pear, because that's how set functions. Each element has to be unique.
So the difference is just that the key double point is missing, and that's why it's creating a set. And it's in, or is it because you use the title?
No, the difference between the dict comprehension and the set comprehension is exactly this. The key is missing. There is no key in it.
And then it automatically puts it in a set and doesn't put multiple of one.
Exactly. So we have the generator, we iterate over it and only get the unique elements out.
But it creates a set, but it treats fruit list not as a set. So it iterates over the fruit list for each title still.
Yes.
Even if they're double.
Yes.
Okay.
So we will see apple twice, but we will only keep one of those apples.
Okay, thank you.
All right. Okay. Let's go down a bit to context managers. So we have managed resources like the memory, which is freed up when the garbage collector sees that we don't have any reference to a previous item anywhere in the future. And we also have unmanaged resources like files and network sockets. And these unmanaged resources can cause some problems if you are familiar with C, C++, Java, and the like. When you open a file, you are always instructed to close that file as well at the end of the running process, because otherwise it can leak outside. And the space that has been taken up in the memory won't get freed. Sorry. So if we try to go over this, let's see the example that I was talking about. So we open a file to write. This is the syntax that we use to open a file for writing. If you would want to use it for reading, you can replace it with an R. If you want to read it binary, you can add B. So if you try to, oh, it's already open. Where did I open it? Yeah, you cannot open it without closing it first. So I think I have opened it somewhere and did not close it, maybe. Anyway, this will also close. Yeah. I'm sorry. Yeah, this is here. We need to close the previously opened file. And then we can reference or create a new file handler, and we should close it before we try to reassign it with anything afterwards. So that the file is not getting leaked. So if some kind of error comes up while we are doing things with our file, so we open it up to writing and we try to write things in it, but maybe we call a function in the meantime that raises an exception. We won't get to the closing of the file, so memory leaks will happen, or file leaks will be happening in that case. And that's why it's good to try and accept and use the finally close that we've talked about yesterday to always close up the file that you have opened. Because finally will run even if an exception occurred. To not be this, don't have to deal with this, Python provides you context managers, and you can manage your resources with the with keyword. And this does that you can open a resource. For example, in this case, we open the file, we give it some name. It means the same as creating it like this, just it will be managed, which means that inside this namespace, you can access this file handler, you can write in it, you can do other things inside. But once we go out of this managed section, so we go back to this place and we try to, there is a code block for that. So if we try to write it outside of the managed part, then we will get an error because this with already closed the file for us to prevent any kind of leakage. I'm stopping for questions. But if
I have a question. So if
Yeah.
you want to open it later on, so you want to use the file later on in again, you have to open it again with.
Yes.
Oh, sorry, I heard it. Okay.
Yes. If you want to keep it open for a long time, you can do everything inside the with block. So you can write any kind of other code inside it and only go outside of this managed part when you are done with your file modifications. But otherwise, you could also open it again. If you want to open something up in a way that it just appends new things at the end of the file, you can open it with A, so it will append to it and not replace the contents of it completely. That's what write does. All right. You can also define your own context managers if you would like. These function similarly to open, and you define that so they can work with the with keyword, and when you create it, you pass the resource that you want to manage, or the file that you want to open, or the path that you want to access. And when you create it inside of with, it will go into the enter method, and you can access the value inside it as D. That's the managed resource in this. Or if this would be a file manager, then you could return the file handler here. And the exit can take multiple arguments, and we could actually define it such that it can notice if some kind of error happened while the exit process. So, and we are going out of this managed part, and you can get access to the exceptions that would be raised during that process. Again,
excuse me, isn't
yeah.
this pretty similar? Isn't this pretty similar to the decorator wrapping?
Not really. I'm trying to see where you are coming from with that.
Because it also
It
does
also
something
modifies.
with the function. So it takes the function and wraps around the. Also, it modifies the function itself. So that's the difference.
It is similar in that sense that yes, we modify how something works, but the main thing here is that we have a setup and tear down process that can be managed within inside this context managed block. And in that sense, it's more like exception handling with the finally keyword added to it.
Okay. Thanks.
So again, you probably don't need to write context managers for yourself very often, but you do need to use it probably more often. And it's worth to remember this with keyword, so you won't get any kind of issues. It can also be very useful if you want to have some kind of final things written into your file at the end, even if some kind of error happened, or if you stop the running of your code manually, but you want your file to get all the dumps that you want to put into it until that part where you interrupted the code. So what I'm trying to say is that it does not just protect you from these name errors and such, but also keyboard exceptions as well when you manually stop something. All right. Then we can go to the last part, which is functional Python with map, filter, and reduce. You are probably already familiar with reduce because you had to implement a reduce function for one of the assignments already. And we will talk about the not built-in, but you can access it via functools function that's already in Python. All right, let's start with map. Map takes two arguments. It takes a function and it takes something that it can iterate over. So, for example, a list. And it will map, or it will apply the function to each of the elements in that list. So in this case, we will double everything in this list, be it string or integer, and we don't have to create a for loop and inside it call the double for each of the elements in the list, but we can call the map function and it will return a map object, and you can convert that into a list. And as you've seen previously, you don't need to define a function with the def keyword. You can use lambda functions just the same inside the or lambda expressions just the same in inside map, because they are functions. It will be ran the same. You can use or you can define a class as well, which implements the call method. And if you have a class that implements the call method, it's callable, so you can use it as a function. If the instance, you can use the instance as a function, and you can pass it to map as well. Here is a different rendition of this. This will create a map object. And you can convert it to a list or a set, same way as you can do with generators. You can iterate over it again, just once. So if we would say is a map, and we want to go over every element in this map, print out its value. But if we try to do it again, nothing will be printed because we've already used up every element inside map.
I have a question about the callable classes. Would it be a common thing to do this, or is it just possible?
That's a great question. And there is one particular example that I can think of at the top of my head where I've seen a call method implemented for class, and it has been widely used. And that is in deep learning. PyTorch uses this. I think PyTorch.
Okay, thank you.
So it comes in handy. All right. So you can see that this map object it functions like an iterator because it is. Any questions about map? All right, then let's go to filter. Filter requires the same. Filter is a built-in function, just like map, and it requires the same things. So it wants a function or something that is callable as the first element or parameter, and the second element should be something that it can iterate over. And as the name suggests, it generates something that is filtered using the parameter function. So in this case, we have this function is even. It should return a Boolean. And it returns true if the number given to it is an integer. It returns false if it's not. And using filter, it applies this is even function to every single element in this list. And if this is even function returns true, then we keep that element. If it returns false, then we don't care about that. Again, you can use it with lambda functions as well. And yes, you can define, so you can write comprehensions, or instead of comprehensions, you can also use map and filter. Remember, previously I used the filter word for filtering out things in a comprehension or in a list comprehension. That's because you can actually use the filter keyword instead of using this syntax. And similarly, you can use map if you want to just iterate over list elements and apply some function to it. So if you would try to use this list comprehension, it can be switched up to using map instead. Now zip. Oh, yeah.
Is there any upside or downside on which way to go, or is it just a matter of taste and coding style?
I'm not sure about this. Maybe the time complexity of these functions is a bit less, but I'm not entirely sure about it.
Okay, thank you.
So before we talk about reduce, let's just give some mention to zip, which takes two parameters. Both of those should be iterable, and it pairs them up. So the first element will be with the first element, second with the second. If it would get two different length elements or two different length lists, it will zip together only at the same length as the shorter iterable.
Is there also the possibility of recycling?
Sorry, can you say that again? I didn't hear.
Is there the possibility of recycling? So when the list 1 has only 3 elements, that I recycle the elements as long as I have as many elements as in list 2? Because now it stops after 3 iterations, but can I, let's say, start again over in list 1 with apple and plum, so to make it in the end a result of 5 elements?
You would need to define a different list for that, and make that list the same length as the other list, and fill up the missing parts with however you would like. So if you would want to restart it from apple again, then you would have to define it, but there is no easy way of doing that.
Okay, thanks.
But you can do it, of course. With list comprehensions, it's the easiest. Okay. Where was I? So you can zip together multiple iterables. You can give it as many as you like, and it will run for the length of the shortest iterable. And you can use it for a bunch of things. You can generate dictionaries with it if you would like to. If you have like 2 lists and want one of those to be the keys, you can create it with 1 line of code and using zip. You can
maybe one question: what does the star mean in the zip call? Because zip should have 2 parameters or even 3, but we have just 1 in execution line 96.
Yeah, here. Remember when we've talked about, or at least you did talked about the function and argument, and this can be whatever length. It's
okay.
the same here.
Okay.
So does it unpack it? So if you have more dimensions and it unpacks it, with 1
Yes.
star, it means it unpacks the first layer, and if you put 2 stars, it would unpack everything into and then it would be just a list. Because in keyword arguments you have 2 unpacking operators in the front, and here you have 1. Yeah, exactly. So if you have 1, then it would do exactly what the questioner before asked. So it would unpack it, and then you have two items that you need to give to it.
It will unpack this list if you pass it with 1 star. If you would pass it with 2, it will try to do, or it will try to recognize it as some kind of mapping, like in the case of keyword arguments. So when you have keyword arguments, the mapping is the keyword and the value of the argument, and it would try to understand this the same. So instead of this syntax, we would have some kind of different syntax, like, I don't know, L1 is this, and L2, oh, yes, oh, am I in insert mode? Yeah. So if we have this, this won't work as well, because we will have the keys to deal with as well in this case, but it could be done like this. But in cases of matrices, you want to use this syntax.
But it would work for the 3-dimensional lists, or am I wrong?
If you would have like this 3-dimensional thing, I won't change it up all the way. It will only go into the first layer of that. So it will unpack 1 list, and you will have to deal with the rest.
Okay, thank you.
You can do it with list comprehensions if you want. So you can flatten this out into 1 list if you want, by iterating over it. I will show you an example, and you will see if that's something that you wanted to know or not. So let's say C for row in matrix, or C in row. C is the column. In this way, you can unpack this into a flattened list. Is this something that you wanted?
No, I just wanted, but it's also interesting. No, I just wanted to know if the number of this unpacking operator changes how it unpacks stuff, but obviously 2 stars is something different than an unpacking operator. Yeah. So it's a different thing.
Sorry.
Okay,
sorry,
but thank you.
Sorry for going on a different tangent then. All right. So you can zip together. This zip again is a iterable thing, and you can convert it into a list the same way. And now let's go to reduce. Reduce again takes something like function, something callable, and takes a list. And again, it will apply that function to that list. The difference is that it will use some kind of accumulator. So it will start to go on, in this case, it will go on the first two elements. It will multiply those two together. We will have 2. Then it will multiply that 2 with -1. And then it will multiply the accumulated value with 4. You are probably familiar with this because it was one of the assignments of the first day, I think. And you shouldn't use the built-in reduce function for that. It's not actually built-in, you have to import it from functools, but sort of built-in reduce. You should write your own for that. Also, you can use reduce with additional arguments other than the function and the iterable. You have to supply it, or you can supply an accumulator that will be used as the first value of the accumulator. So instead of initializing it with the first element or the first computation, you will give it a default. This is a different example for that, or how to use reduce. Oh yeah, and reduce takes a function that is not just one parameter function. So the previous functions only took one parameter. In the case of map and filter, you see, like is even only takes one parameter. In the case of reduce, you should supply 2 parameter functions for that. All right, and the last little fun thing is about Booleans and integers, because Booleans, true and false, are actually instances of integer. So true is 1 and false is 0. That gives you additional functionality to it, so you can add together 2 truths, or you can convert it easily into integer if you have to use it for some functionality later on. And I think this is it, and we didn't run out of time that much. Any questions?
I have a question in regards to context managers.
All right.
It's a dumb one, but
No. There are no dumb questions.
In the keyword with, like, we can define a context manager as a class, but we have used the method open with the keyword with, and it closes the resource. But it's a method. How does that work?
We should go into the implementation of open to see this.
Okay.
Can we go into it somehow? I don't have it open yet. But yeah, that's an implementation detail, and Open can handle this and functions that can open sockets, not just files, can also work with the with keyword.
Okay, so it's an exception, like that wouldn't be used in production. Like we would, if we were to define context managers, we would use it. We would do it with a class. Like it is never used with a method.
It is used with methods like open and socket.
But those are exceptions.
Function.
Like
yes, and you could look at the implementations of these functions, and because they are available, and you can see, or you could take them as examples if you would like to define something that works with.
Thank you.
Could you also use a callable class there and call it as a method?
Yes, you can use with a class there, if that class is a context manager, so it has an enter and exit function defined. I don't know what else to add to this.
So that you use a callable.
No, it
function.
doesn't have to. No, it doesn't have to be a callable class if you want to use it.
No, but if you can use a callable class with it, with.
Yes, you can. Just make
so
sure
you don't
that you
need
have.
You don't need to instantiate the class. You can just call it in with.
No, you do have to create an instance of it, but you can call that instance if you want to use it inside.
Okay.
I will stop the recording.